Okay, shall we start? How are you, everyone?
I'm okay, Sensei.
Yes. えーっと、okay, let's see. Let me start first. えーっと、えーっと about the coupling wall, I would like to explain first. By the way, I tried to contact Muhammad Yabas-san, but he doesn't reply
Oh,
to me.
Sensei, Yawa-san have a Matsumoto Sensei class today at 1 p.m.
Okay.
Okay.
Zafira-san, you are still in Malaysia, right?
Yes, I will go back this Sunday. My flight is
Ah,
this Sunday.
えっと、so I want to, how to say, explain again. Yeah, this is the material I explained before about displacement-based design. So, so we discussed about putting damper in the middle of the coupling beam. And first we conduct pushover. Yeah, and so we obtain the equivalent single universal freedom system by pushover. And first we try simple beam, steel beam without the damper. So we find yielding moment happens, and yielding happens at both ends by flexure yielding, and the yielding moment is Ny. So we know shear force at that moment is at this Qm, and force yield moment divided by the length of the beam. So we try to design the damper to be less than this value. So for example, 25% is 0.25 multiplied to n. So this is the damper strength. So if we push the building, damper start to yield before beam yield by friction. Yeah. We try to I mean, how to say, we try to dissipate energy by damper. So damper must be weaker than beam. So we start by changing this factor. And the target is under large earthquake, we try to limit this deformation, story width. So first we set target story width. So in this case, 1 over 250. So under 1 over 250, it means because the story height is 320 centimeters, so target story width is 1.28 centimeters. Okay? And by this push over, step by step, you can get the relationship against the story drift of each story. There are 1, 2, 3, 4, 5, 6. How many? 7? Right? And so there are many lines. So this is the story drift of each story. Okay? And it is getting larger. And the horizontal axis is the displacement of the equivalent single linear freedom. So we want to find out when story drift reach target story drift, 1.28 centimeters. So we decide this deformation. Then we found, I think this is the 10 story. No, 40 story. Maybe this is the, I don't know, 8 story, 7 story. Anyway, top story. And at that moment, equivalent single linear freedom this deformation is about 7.663. Okay. And this is the relationship of single degree of freedom, deformation, and shear force. Well, shear force divided by equivalent mass, so this is the acceleration. Anyway, and 7.63 is this point here. So this is our target. So we want to design this building under large earthquake. The deformation is less than this target. So and we want to know how much damping we can expect for building equivalent damping at this point. So we must know the ductility factor of member at this point. Yeah. To know the ductility factor of the member, we push the building up to this target to displacement, and we check the ductility factor. So, yeah, so we push the building. So this corresponding to the top deformation is 11 centimeters. So we push this building until then. So this is the target. We push this building basically up to target displacement, and we check the damage of the building. Yeah. So this is the damage of the beam, and we know that the factor of each beam and the coupling beam, and this is the damage of the shear wall. Yeah. The bottom shear wall is the most damaged. Then we can calculate damping factor for beam by this formula. This is a bilinear formula. Damping, equivalent damping for bilinear hysteresis. Okay. And this is the equivalent damping for wall element from freestone. So after getting each damping equivalent damping, finally we calculate total equivalent damping. Yeah. Sorry, it's not written H, so it must be maybe H. So now we know how much damping of the single freedom at this target deformation. And from now we are talking about earthquake. Yeah. This is a design earthquake. And so right one is the acceleration response spectrum of life safety earthquake, damage control earthquake, subunity earthquake. There are three levels. And if you below deformation spectrum, left one, life safety, damage control, subunity. And this spectrum value this is plotted by damping is 0.05, 5% damping. But we already know the damping is more than 5% because we have damage to the member. So we must reduce this spectrum according to equivalent damping. So this is the equivalent damping is 5%, 10%, 15%, 20%. This is the acceleration, and the right side is the displacement. And this is equivalent damping 5%, 10%, 15%, 20% for design spectrum. But anyway, if we know damping factor, for example, about 20%, and if we know target to deformation, we can get equivalent period T. And from this equivalent period, we can get equivalent to omega, circular frequency. Then we can get the effective stiffness. Yeah. finally we plot target group multiply equivalent stiffness, then we can get red point. So this is the estimated response of single degree of freedom and the large earthquake. So we know this shear force is larger than the shear force of pushover. So it means, how to say, uh, we, uh, we must reduce the coupling beam size so that we can reduce shear force of this estimation. So we reduce from red to, no. We change this blue one to be more close to this response. Yeah. So, so if we reduce coupling, really? This is the redesign. Okay, not to reduce. Maybe in this case, we must increase coupling beam. For example, if this is 0.25%, maybe we can go up to 70%, maybe. So after repeating this process, finally we can obtain the optimum amount of damper. Yeah. So this is a procedure. Now I want to modify this procedure for viscous damper, and I found that Stylus really doesn't work if you put the viscous damper here. Dr. Maybe you tried.
Ye- Yes, Sensei, I try. It doesn't work properly like metal damper.
Yeah.
Yeah. Uh,
But if you found the problem, please send me email.
okay, Sensei.
I think you noticed uh,
I
maybe
mm, I was trying so many different models, Sensei, to compare is there any wrong in my step, but I think it's not the problem of the properties. Maybe because of the Stera 3D. Now,
yeah.
yeah.
So, I found 2 days ago.
Mm.
Oh, the program doesn't work if you put this sample here. So I'm now fixing.
Okay.
Maybe please wait
Okay, Sensei.
this weekend. I will
Mm.
fix. Anyway, now the procedure is same. First, you have a coupling beam, and you do pushover, and you can also get the equivalent degree of freedom, and target drift is same. Yeah. And this is the target point. So, we want to know the damage of the element at this target displacement. Yeah. So as we did before, we push the building up to this target grid. But in this case, because it's a static analysis, this cost damper doesn't resist against the static because it resists against velocity. So zero velocity, so zero shear force. So only you can get the damage of wall because you cannot get any damage of coupling beam. So you can get the damage of wall only. So how to get the damping of beam? So this is different. Yeah. So hysteresis element is only wall. Yeah. So there is no hysteresis damper. We have a viscous damper. So viscous damper, you must calculate velocity. So suppose this is the target group, and you can get the equivalent frequency omega from connecting from bottom to target group. This slope is omega square. And if you can calculate omega,
Mm-hmm.
you can calculate velocity.
Mm-hmm.
Yeah. So, but you assume some sine or cosine, response, actually, harmonic response by frequencies omega, then you can get the velocity. Velocity is if you uh, take a derivative by time. Yeah. So the damping force will be c multiplied. So this velocity part is omega a cosine omega t, and power of alpha. So this is because viscous damping is c multiplied velocity power of alpha. Yeah. So this is damping force. Then you must calculate one cycle damping energy by integration. So this integration is very, very complicated. So if alpha equals 0, it is very simple. Integrating one cycle of cosine. Yeah. So if alpha equals 0, this will be 4c amplitude A. Very simple. If alpha equals 1, it's also possible. It is a cosine square of cosine and the integration. So this will be like this. But if alpha is 3, 4, 5, in general, it's not so easy to integrate this function. And Professor Kasai proposed simple formula, this one, and phi is 4 under exponential function and power of minus 0.24 alpha. So this is not exact なんていうのかな、value, but good, very good approximation. Anyway, so we can use it. And so this is energy. And that, なんだっけ、the definition of damping is, as you know, definition of damping is one cycle energy divided by potential energy, triangular area. Yeah. So if you divide one cycle energy, delta omega W, divided by potential energy W, and also divided by 4 pi. So this is the definition of equivalent damping. Yeah? So now we success to calculate one cycle energy by which formula? This one? Yeah, this one. Yeah, one cycle energy. And the potential energy here. So you can get the damping of the viscous damper by this formula. Yeah. But I'm still thinking how to get M, because the damper is arranged every story. So, but M. So this is the case of only one degree of freedom. So if we have many dampers, I was thinking how to get this potential energy. So, and if we have n damper, maybe this will be some engine. So I didn't finish it.
Okay.
Anyway, if I get the damper of viscous damper, and we already know equivalent damping of shear wall, so in total damping of structure will be square root. So it will be something like this. And yeah, something like this. So this is a damper of hysteresis damper, and in our case, this is the equivalent damping of wall element. And this is the equivalent damping of the viscous damper. So we took the square root, and this is the initial damping, maybe 5% or 2%. You know. So it will be total damping. So I'm thinking to use this formula. So this formula actually proposed by Naki-san and myself. Uh, so anyway, so and after you get the equivalent damping, the procedure after that is the same. You use the design spectrum of the earthquake, and if you damping, you can get the equivalent period from the target displacement, and you can get omega, and you can get the red point. And if red point is higher than your capacity curve, you somehow change damper. In this case, viscous damper capacity to be close to this red point. Yeah, so this is a procedure of uh, displacement-based design in case of viscous damper. So, anyway, I believe it works.
Okay, sensei.
Okay, so sorry, I didn't complete this manuscript document. So after I finish, I will send you.
Okay, sensei.
Any question from
Mm.
any question?
Sensei, the formula for the W, there's A. Is that the area under the graph?
So your question is about
This one, sensei. W, the maximum potential energy. They have A. Is it A? Is the area under the graph?
A is how to say
This one.
and you push the building up to target displacement.
Mm-hmm.
Okay, so amplitude of the building, I mean, at this target drift, it will be A.
Okay. Okay, sensei. Thank you so much.
So I was thinking how to get to M.
Is the mass? Is it mass at every floor, or is the average mass, or a mass of the temper?
Yeah, this is what I'm thinking now.
Okay.
How to do.
Okay,
no,
sensei.
no, no idea so far.
Okay, sensei.
Yeah. So if you have a good idea, please tell me.
Okay, sensei.
And Zakura-san, do you have anything you can?
Yes,
show me
I
today?
can share what I did for this week, sensei. Okay. So basically, this is my slide. So first of all, I try to understand the visco temper by the wall. So this
Yeah.
is what we discussed last time, and I try to apply by viscoelastic by a
Okay. Could you go back to a picture of
this one.
damper?
Mm-hmm.
And so this is a oilless
From oilless.
viscous damper wall.
Yes.
And there are single type and double type. Okay.
Okay.
So in case of single type, so there are three plates,
Mm.
and the middle plate is moving between, I mean, inside viscous material, viscous fluid,
Mm-hmm.
and the displaced energy.
Yes.
Right?
And if you can see double type at the top plate, they have two, so they'll call it double type.
Okay.
Mhm,
So
okay.
we can make double, triple as we want.
Yes. It depends on how thick the wall it could be. Okay.
Okay.
And the third picture is how they install in the structure. So this one attached to the top floor, and this bottom attached to the floor it is. And then how it worked, the damper mechanism, basically when the earthquake like attack the building, the bottom wall will go to the left and the top one will go to the left, and that is how they dissipate energy. And then we can design the how much we need for the thickness of the fluid and the thickness of the metal by using this formula. Basically, in the reference, they use this formula by Euler's. They propose this formula. So F equal to 5.56, and others they use different numbers. And also alpha here, if you can see alpha here, also different based on the design. And then, first of all, we have to know the surface size S.
ザクラさん、
Yes, sensei.
you must put so 0.04 is multiplied by we divide by
Oh, this one. Okay.
you must put blanket.
Okay.
Yeah.
Okay.
Yeah. And actually, this damping force is also function of area of this
Mm,
wall.
yes.
If area is very large, you can increase damping.
Mm-hmm.
And also, this is a function of temperature. So this is different from hysteresis damper.
Mm-hmm.
Hysteresis damper, we don't need to care about the temperature,
Mm-hmm.
but this viscous fluid, the material is very sensitive to the temperature. Yeah. I remember when when I was in Building Research Institute, Professor Kasai used structural laboratory in Building Research Institute for testing viscous damper, and it was winter, very cold. So he want to heat the damper. To keep the temperature 20 degree.
Mm-hmm.
So he put some なんていうのかな、plastic bag around damper
Mm-hmm.
and put hot
Hot water.
air
Oh,
inside.
hot air.
Yeah. So
Mm.
it's not so easy to keep same temperature.
Sensei.
I remember. Well, anyway, so this is a formula of this viscous material, damper. So we now use this material for our coupling pin. So the difference is we cannot get this kind of very huge area. In this example, almost 3 meter area, very huge. But when we put the coupling pin, maybe the size is very limited. So, but we can increase layer, right?
Mm.
Double, triple. So we can somehow, how to say, compensate. Small area by increasing number of layers, maybe.
Mhm.
Okay. Anyway, please continue.
Okay. And this one, I try to apply for beam size. So basically, the basic formula is Fc equal to C velocity and alpha.
Yeah.
And then I will try to find how many force they can attain by one layer. So basically, we just try one layer equal to 5 mf thickness of the fluid, and the area is about 35 times 30 centimeter.
Okay.
So the total area about 1050 cm square.
You adapt 35 from this picture, right bottom.
Right bottom. Yes, sensei.
Oh,
Here, right,
okay.
just
30, okay.
centimeter square.
You need a square.
Yeah.
Yeah.
Yeah. So then in Stera, if we open Stera TD here, we can see in here we can set if we choose steel material, and we can change the shear spring, and we can select viscous, and we can input the data. We need stiffness and damping coefficient and exponent. Exponent is the alpha. So these three component that we need in our stereo TD. So basically from here we estimate the area that we need that we can apply to the beam, and then we can get C, which is 25.5, and then we can calculate velocity.
So you assume 20-degree temperature.
Yes, 20-degree temperature. Mm. And then we can calculate velocity based on the C, and then from the V we can calculate the force of each damper. So for one layer we can take 15 kilonewton. So for example, the damper for the whole structure, each of the beam, the maximum it can take is 400 kilonewton. So if 10% is 40, so we can use one layer. If we want to use 25%, which is 100 kilonewtons, we can use two layer, and so on. If we use 50, we can use four layers, and if we want 75, we can use six layers, which is we can get around 300 kilonewton. Yes, we cannot.
And
Yes,
velocity
yes.
5 is actually very small, maybe small earthquake.
Um.
How
Oh,
much deformation of
velocity is
coupling beam?
is based on here, sensei. For the velocity actually based on the thickness. So for example, our D is 4 mm, and V over D is 10, and the velocity is fixed. It's always 4 centimeter per second.
How you get this number 10?
From here, sensei, we cannot use this one.
Actually, this formula
Mm-hmm.
doesn't. You don't need to care about the velocity.
Okay.
And this is very small velocity. They change the formula, three formulas.
Mm-hmm.
But also they propose only one formula
Mm-hmm.
for any velocity.
Okay. So, okay, sensei.
Actually, let's see. ちょっと待ってね。Let's see. Suppose if we have a building,
Mm-hmm.
okay, and acceleration is 300 bar.
Mm-hmm.
So this is a large earthquake, and the response is okay, it's 750 bar, for example. Okay. And the building natural period is suppose 1 second. Okay. So this is the acceleration of the building. The velocity is A divided by omega. And omega is, in case of 1 second, it will be 2 pi. So it is around 6. So it means we can expect velocity around 100 centimeter per second. So in your case, you assume only 4.
It's too
So
small.
you can expect 25 times.
Okay.
And could you go to next slide?
This one?
Yeah. So this is 25.5. Okay.
Mm-hmm.
So this part is 25.5, right?
Yes, sensei.
And alpha is
0.44.
So from this picture, so I believe this will be this kind of curve.
Yes, sensei.
And this is velocity. And this is damping force. Could you draw this curve from this? I
The
mean, this function. Could you draw?
in Excel.
Yeah. Data.
Okay,
Data.
sensei.
So you will know in case of this is 5, you said this value is around 51,
Mm-hmm.
right?
Yes, sensei.
And in case of 50,
Mm-hmm.
you will know how much it will be.
Okay.
So this curve is necessary to how to say uh, to know the how much damping force.
Okay.
So please draw this curve,
Okay,
and
sensei.
also you can draw this curve one layer,
Mm-hmm.
two layer, and three layer. So maybe you can draw velocity force relationships for different layer.
Okay.
Okay? So please draw this graph.
Right.
Yeah.
Right. Yes. As you mentioned, I think the strategy doesn't work. So I tried to run for time history analysis, but I think the story drift doesn't adequate with the target drift 1.28 centimeter. Mm. So
So this is a result of time history,
yes, sensei. For
but time
artificial,
history also doesn't work, right?
yes, I think it doesn't work because
How did you get this time history?
uh I just put here after we run
Uh-huh.
and
What
here
damper in the middle?
the middle is the based on the properties that I calculate from the viscose here. This one.
It works.
It works.
Maybe it doesn't work.
Yeah, it doesn't work properly because if we use metal damper, we
Yeah,
can
it looks working, but the program has, I
problem.
mean, bug.
Okay,
So
okay,
don't believe the result.
okay,
I will fix it.
okay, sensei. Okay.
Sorry.
It's okay, sensei. And then I also found one paper that I sent to you about experimental validation of viscoelastic coupling damper, and this they have
Could you go back? Could you show me the picture of the damper?
this
Yeah.
one.
So,
Okay,
what is this?
okay. They have two damper. One,
Uh-huh.
this one.
Yeah.
I think this is deformation, like deformation in for the viscoelastic is like how the viscoelastic deform, like one with
So
one
before deformation, it is how to say
going up and
over
down vertically.
or is it designed in this way? I mean, before deformation.
No, no,
So
sensei.
I don't
Be,
know why it is so separated in the
I maybe they just want to show us how the damper how can I say deform. The original one is like this,
Oh,
and if I can open the paper,
yeah.
it's depend on uh the loading exists. So for example here they pull one up and down. If you can see here the C diagram, this is how it deform. But if in the structure it will go one up and one go down. It depend on the direction of the force, I believe so. Mm. So
Okay.
this one is up and one is down. So it deform like this.
Mhm.
So it depends on the direction of the force. Mm.
Mm.
So in this paper, they have same viscoelastic. The
Mm.
different only that the B type they have fused at the end, both end of the viscoelastic damper. This is the normal type, but this one was applied for 85 stories, and this
Mm.
one for 50 stories. Yeah.
Mm.
Mm.
Okay.
Yeah. So I try to use the properties as they share here to apply in sterility. I think we have to fix sterility first. Yeah, I believe. Yeah, I
Uh,
try to run with time history analysis. The
Uh,
shape is.
do you
Mm.
think it's possible to compare this damper with oilless damper? Can
Uh,
you compare?
if I can give some comment that after I run this, the shape is almost the same.
No, 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 no. Don't believe the still 3D.
Compare the numbers here.
Yeah, yeah. Compare the C value
Mm.
or alpha.
The alpha, they doesn't give alpha here, sensei. They only give K and C, but the value of K and C is quite different. For example, I give you 75%. Okay, 75%. For C is 154, but for K is 31. But for the paper, the C is much more smaller. Yeah, 26. For example, this for higher strain at amplitude, the C is much more smaller compared to K. So I think it's different material and it's different properties.
Okay. So and there is no alpha.
Ah,
Why?
there's no alpha.
Why there is no alpha?
Hmm. They use this formula, like basic this formula.
Oh, okay.
Yeah, so they
So,
doesn't use
so
alpha.
velocity there, there is no power of
Mm.
alpha.
Yes.
Mm, okay.
So yeah.
Okay.
Okay, sensei. That's
Yeah.
all.
So after I fix Stella 3D, you can
Try again.
uh, compare again.
Okay, sensei. Thank you so much.
And Sarah-san, do you have anything you can tell me today?
サラですかサラニャですか
Huh?
サラです。
Sarah-san.
あ、
はい。
はい。わかりました。あります。
はい。
Can you hear my screen? Okay. First, I'm gonna talk about wall. I'm gonna talk about wall elevation before starting the coupled wall, and there are three main categories of structural walls, and first of all, A is cantilever wall. It is suitable for seismic resistance. It is because it is um, because it is in elastic action occurs in the flexural plastic hinge forming above the base on the wall, and above the region the wall remains inelastic.
Okay.
Okay, and above the wall with the openings, it is unsuitable for seismic resistance. Generally below the first floor, as indicated by a shaded area with proportions showing, it is very difficult to avoid an inelastic action occurring by flexural yielding or shear failure in the piers. And the final one is the coupled wall. It is the most suitable for seismic resistance, and it is designed to form flexural plastic hinges at the wall faces and in the coupling beams like this shaded area, and this provide an efficient mechanism of resistance resisting seismic forces with the reducing displacement. Okay, and about floor plane of coupling beam, coupled wall, it is typically occur in the configuration such as where two symmetrically oppositional shaded walls in close centralized facilities such as uh, elevator, stair, and toilets, and link it at the floor layer by beams. And in addition, coupling beams have low aspect ratio and long of coupling beam divided by height of coupling beam, and L is the distance between the central line of this wall 1, 2, and wall 2, and H is the coupling beam height of coupling beam, and this and the most important things are these equations: moment of coupling beams, shear force of coupling beams, and the first of all, moment of OTM. It is this picture as indicated by this picture. It is easy to understand. Moment of OTM. Moment of wall 1 plus moment 2 and plus TL. T is total shear force of coupling beam, and L is the distance between two walls. And after when the lateral force applied with the couplet wall with the structure, the first force is going down, and another other force is going up, and in this picture shown as and second one is mechanism of coupling beams. In this picture, the force is this force is down and this force is up, and as a result, we can see coupling beam in diagonal crack. In this
What we call shear crack.
shear crack.
Yeah, shear crack. So this cup, left side is going down and right side is going up. We call this deformation shear deformation. Okay.
Okay. About B, it is very windy, and this connecting between the beams and walls is not strong enough, and it can cause failure like in here. Above C is reinforced, so they put a very strong bar, and they are going to direction to indicate the false direction in the carbon beam. Okay, that's it.
Okay, very good, very good. So, yeah, you are just a beginner of studying coupling beams. So, very good. So please continue.
Okay.
Okay, good. So now, Ataya-san, your turn. Okay.
One model of very well. I suppose I assume that we as I mentioned, 28 meters per meter.
Mhm.
And this is very high pressure because here, according the standard law, standard law, the meter. So each flow has 6,720 kilometer rate.
Mhm.
And also I found this formula in a paper
Mm.
that was reference to the building standards of Japan.
Mm.
If in or T, then alpha is equal to 0, and we can find the fundamental theory of the building is equals 9.2 the fundamental index equation mostly for all. And for finding thickness specific theory, again I used this formula because I couldn't find any better formula. After analysis of that twin story building on the center instance, this is the result. The black line is for without CND and second one is without CND.
How many TMD you put?
3 CND without the effective mass ratio contribution of the first model equal to 92%. So that is enough because if we add another CND, for example,
Could you show me how much effective mass in case of 20 story?
uh,
So first model is not I don't know how much.
uh, 0.7
0.7. I couldn't see. Well, 0.76. Okay.
and second model 0.9.
Okay.
Um, if we add another PNG, we will not obtain better results in that PH because the first mode mass contribution is small and there is no need to concentrate.
There's, I have a question.
Yes,
And so you have a building, right?
yes,
And you put one TMD.
yes.
And in case of 2 TMD, one is at the top, right?
Mostly, yes.
Mostly. And another one is if you calculate second mode, and you put the most largest deformation, you put one TMD here,
Yes.
right? And
Yes.
how do you calculate the stiffness of TMD?
Uh, yes, PMD is omega 3 differential 2 multiply
mass of TMD.
yeah, maybe
Oh,
okay.
so omega is not the first mode. If you put the TMD in the middle, you use frequency of second mode.
Yes, okay.
Okay.
And the third mode also frequency of third mode.
Okay. But the stiffness is soか. So effective mass of first mode is very large, so the stiffness is still large compared to other.
It depends to the method of mass distribution.
Uh-huh.
Example, in this case,
yeah.
it's not dot.
Okay. I see. Okay. Do you have this Excel file for 7-story?
Yes.
Could you send it to me?
It's a little organized, but for 7-story, that's a little file is not too organized.
Uh-huh.
But I will make it organized.
Okay, so after you organize result, please send me. Ataya-san, where are you now?
I'm in the lab.
Lab? Oh, really? But it looks your connection is not so good. I don't know.
Today I don't have webcam, and I joined this lab desktop and also with my smartphone.
Okay.
So since this is the result that the displacement of building with TMD over and controls
So if this value is small, it's good, right?
yes, okay.
So it looks which one is good?
Single TMD is good, and when the mass distribution is done based on effective mass ratio is the same as single TMD, and this is the product of effective mass ratio and participation factor, which is the second good result. For equal mass is the
Maybe
worst.
you should show me the graph instead of number. So this is a result of no TMD, right?
Yes, okay.
And which one is single TMD?
This yellow line.
Yellow line.
Yes.
Okay.
The most good.
And what is black one? No. What is this color? This is no.
This is the effective mass ratio.
Effective mass.
Yeah.
But
And it's based on modal mass. And the rest is based on product of effective mass ratio and participation factor. But the green is the equal mass for each TMD. It's not good.
Okay.
But because maybe the displacement of TMD is also calculated and the result of zero. This top displacement or not real displacement of TMD.
So this is a case of El Centro.
Yes, okay.
How about the other? This is Kobe.
This is Kobe. In Kobe, the product of effective maturation for station factor gets better, the most good result compared to the others. Others are somehow equal, but if we see in the numbers, we can see the differences. The product of effective mass ratio and participation factor is the most small numbers is good result. And this is on the top. Again, the product of the effective mass ratio and participation factor has given better results. And on the Sudoku, it is very reasonable in the product of effective mass ratio and participation factor has given
Why there is sudden change here?
Because the displacement of CMD also, because CMD which is model has also the same height as the building height. So the damping is small, so the displacement is small. If somehow the stroke length of the CMD is also calculated by itself.
Could you explain which floor you put TMD?
The top floor, which is 20 story, the 19th floor, and also the 16th floor.
Could you explain again? 20?
19 and 16.
20 and 15?
16. Yes,
15. So around here.
yes, 16 is here. 17 is attached to 16, but it has the height up to 17.
So, but you have 3 TMD.
Yes, it is 3 TMD.
So 20, 15, and one more. Where?
20, 19, and 16.
19?
Yes, it is.
It's almost equal to 20. Why it's
Yes,
so close?
Because the largest amplitude of second model also 20 because we already installed the TMD, so we consider the second grade amplitude of multi-chip, which is 19.
Could you show me the model shape?
Yes. This is the mode shape.
Why don't you put the damper here?
It is possible, but this amplitude is larger than this.
But you already have one dump TMD here. So why is it necessary to put another one also here?
So it's in the top and another is in the lower floor.
It's only one story.
Yes,
You must think about another technique maybe. Maybe I think it's reasonable to reduce amplitude here.
yes,
Third mode may be possible here or here.
Yeah, it is. Infection levels, the amplitude of moisture fire, so I made it.
So could you try changing the location?
For the second mode there,
I don't know. So it's also part of your research. You can propose some new methods how to arrange the location. I think it's not too reasonable to put the TMD so close to each other. Because this second TMD also contributes first mode. Definitely.
thing because uh, it depends on the tuning, the frequency.
No, if frequency
Example,
is
uh, for example, if I do the you can see that only the top CNC vibrates. They can move it because it tells the specific rhythm of that CNC. As much only this CNC shows the top CNC don't contribute. Versus also from the CNC itself voices the so each CNC don't contribute and the mode shift vibration of the mode vibration of each note.
but Narayana, how do you think?
Yes, Sensei, actually, according to the mode shape values, I think this is okay. But I also agree that these cells becoming too close to each other. We don't know how it is.
So, well, the I mean, optimum location of KMT is also one research topic.
The reactance against
For example,
human
you can move location gradually lower, and you can check which one is most effective.
rotation uh,
Well,
okay.
even if, please try. You put another peak lower.
Rotation
Uh,
uh, reactance against the Toronto that we can say that this column is or smaller than other column. Uh, that the navigation concentration factor given good agent even greater than the CND and then on the storage around it not center it at
so it's tough.
on
There is nothing on that. But it looks very similar. Okay.
uh, versus the not influence the center center for seven story also got the same too. Uh, when story finish on the four it also half Survey and center. So overall, we can say that the distribution of CND mass is based on product maturation for factor will be federated. It can be seen in the current history as well.
Ay, lambat pula.
Although the preference in clear and history is not too much. All of them or some have equal, but the difference is about 1%, 2% or up to 3%.
Okay.
Uh, but here, about the difference is about 9% or 10% compared to equal mass. Um, and that also can also, I, I don't know if it was in brain model. I think that, yes, I don't know if it is possible.
Uh-huh.
A brain 5 meters by 5 meters, and I added another span for installing CMD. Here the column continues, but we don't have anything else.
Okay.
We install just CMD, and this is the top floor.
Uh-huh. Okay.
So,
Oh, interesting.
I don't know. For example, if it would claim that the displacement of this CMD don't contribute to the displacement of the structure, then the output of CM zero may be show the real displacement of building.
Could you click option structure? What degree and freedom you
I created all just one.
just one. So in this case, the beam doesn't deform at all.
So maybe I will create, I will create
Uh, but if you allow rotation, maybe you will have some error because the damper TMD only.
and all the information is this contribute to CMD
Yeah.
this is for all buildings, I think.
Yeah, all building including TMD. Yeah.
And so if you can model CMD and brain, it will be good because you can find other indicators like damage, like acceleration, and those the shear force.
Okay.
And
So why you want to try plane?
mm, because the brain, as I said, okay, uh, the displacement of each story is real because in landmark model, the story displacement of those story which is CMD as an assault is not real because the CMD has the same height of the building, so the CMD damping is also lower, so the displacement of the CMD is larger than the displacement of the story. That means that when it is rained, the CMD uh, comes out from the building displacement. For example, like this, if you give the TMJ when it's called the inspection flow.
Yeah.
So the height of TMJ is up to 17 floors.
Tuh, tuh, tuh,
So
ke atas.
it's
Atas
the
bawah bawah ke
measurement
atas.
of TMJ, not structure.
Ang kamera ke? Ang kamera ke?
And also in the 19 and 20 floor as well.
Like a champion.
Yeah, still, in case of lumped mass model, yes, as you say, uh, okay, this is lumped mass, and you put PMD height is same as upper mass, right?
Yes,
That's why it vibrates. It looks more than main building.
yeah, because the damping is lower.
So,
Buka tu. Ha.
how to say?
Apa? Tu. Kat tempat bawah. Bawah. Tu yang warna merah tu. Ha. Ha. Ikatnya kat sini.
But the response to mass and
Siapa bawa kita Viva?
Ni kan. Ada
and
siapa?
you
Turun
put
makan.
also dumping.
Ya ke? Ada tadi siapa kita gerak. Siapa gerak? Adik Jess.
And another case is if you put this
Ayah lah kot.
story, for
Ayah
example,
macam ni. Tak ada mat.
and you put dumper PMD here.
Yes, okay. That is when it was red.
But the same mass, right? Same mass, same stiffness, same dumping.
Yes, yes, okay.
So temperature is only height of element.
Yes,
Yeah. So it looks very large deformation, but actually, really, but this deformation, this left one, right one must be same.
you can see as I showed the full share of control stick in your maybe before. Yeah, the mode shift was somehow wrong because the statement of the TMG wasn't right.
But the same mass, same stiffness. So
Like this, and as you can see the control model, the mode shift because the statement of the TMG, the last mode share of control is wrong. And in case of displacement, also this is true. It is mostly after installing TMG. Yes, you can see that it was red and very large problem. Yeah.
what the, it is the same mass and the same stiffness, and it is the frame. The TMD is the same mass and same stiffness. Right?
Yes, okay.
Why deformation is different?
Because this is molded and the outside of the model. And this is drainated inside the frame and it drainates it was this more than uh, then it's better because the height of the PND is small, it cannot come out from the train.
Why?
Because the height is small.
Well, height, but it is a horizontal screen, so you can deform as much as you want. Height is nothing to do with deformation. It's a horizontal
Since
screen.
the lamp mass in the height is important.
But height is nothing to do with the result.
Uh,
It's a horizontal.
so, so why the most product like that?
So this is the mold shape after you put the lamp mask.
Like,
Uh-huh. Yeah, because this is the mold, and only this PMD is activated. So this is not the second mold shape of the main building.
yes, and then it's contributes and the most shape it also contributes and the statement.
So you should examine the mold shape of the main building.
This is the most shape of the main building without PNG junction. And regular.
Yeah, with the change, okay.
Yes, it's PMD
So you
wide.
cannot get all the shape of main building from Sphere 3D.
Yes, it's PMD, yes, you cannot. And this sudden changes also to the screen.
So maybe this part is touching with not the main building, maybe.
Yes,
This is a PMD.
basement of yes,
Okay, okay. Okay. So in this case, you should check max node from outlet of Stella. Um, so how did you plot this result? Do you have an output data of Stella?
yes, it is. And
Yeah, this is the max structure. Yeah. So this is max deformation, maybe the deformation of PMD also. So
yes, PMD is also nice.
could you show me max node? There is a file max node in the folder. Max node. Max node. You don't have?
Mac know that.
Yeah. Max node. Yeah. So you can see maybe this was the main building. Okay. Is this a lamp panel? Yeah, maybe. It's a lump mass model, are you sure? Okay. So this is a PMD. So, for example, in case of four stories, you have a deformation of PMD and deformation of main building. So if you want to check main building, you should check 33 and 34. And could you go down? And you can go down. Stop. Too much. You go up. Stop. Stop. So 34 and 35 is around here, right?
Okay.
So you can get the max deformation. I don't know which one it is. But could you go up? Go up. Stop. Stop. So I think this is a deformation X, deformation Y, deformation Z. So this is a deformation. And this is a rotation. And this is acceleration. So if you want to know deformation, you should check dx. If you want to know acceleration, you should check x on each node. From node 1 to I don't know how many, whatever. So if you check main building, maybe this is main building. Right? But this is I don't know. This is PMD. This is just a tool. This is a top PMD. Yeah. So if you check 66 or 67, you can get the deformation of the main building.
So you end up using Rice.
So yeah, 6. Yeah. The deformation of main building is here. So you can plot this. Do you understand?
Yes, I will take it.
Okay. So
Not right.
yeah. Okay, good. So first, please think about changing the location of DMD, and I want to see the result again. Okay,
Yes.
and Saraya-san, we have a discussion with you separately, maybe. But if you want to say something here, well, do you have anything you want to?
Not today, maybe from the next.
And yeah, I will discuss with you next Tuesday. What you will show me at that time? Do you have a building model, right? You have a building model.
Yes.
And if you want to use Stellar 3D, maybe you should make the Stellar 3D model.
Okay.
Okay, yeah. And okay, so shall we discuss next meeting? Yeah, we'll take schedule. And so next week, in Japan, we have a Golden Week holidays. So maybe after that,いつがいいかな。これはあれか、ローカルプレゼントやつを、なんていうの、解散。How about 11? I have a lot of free time.
I'm okay, Sensei.
Afternoon. 1 o'clock?
Okay.
Yes, sir.
Okay. So 11. This is the control group meeting, and I'm not allowed. Okay. Under so 5th of May, it's still holiday. I plan to go to Hamana Lake for sightseeing. So I can take 3 people maximum, the capacity of my car. So Saraya-san, maybe you go.
Yes, sir.
Are you free on 5th of May?
Yes, sir.
Okay. How about other people? Zabira-san, how about?
I already been there, Sensei. You can bring other people if they want. If there is empty, you can let me know. I will join with you. Yeah.
One moment. I must check weather. Yes, weather of if it's raining, we cannot go. 5th of May, raining. ダメだな。Saraya-san, maybe we should stay
Yes, sir.
the day. Yeah, it must be sunny. It's raining. It's not interesting to go outside. Okay. I plan another time.
Yes, sir.
Okay. So anyway, so I will see you 11th of May.
Yes.
Okay. Okay. And Saraya-san, maybe we can have another also occasion also.
Yes, sir.
We meet separately. Okay.
Yes, sir.
Yeah. Okay. 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 See you. Bye
See you.
bye.
Thank you, Sensei.